Good evening, Internet. I am Matt Booyak, and in this video, we'll be taking a look at the 35th problem from the Project Euler Problem Archive. Now, this problem asks us to find all circular primes less than 1 million. And it defines a circular prime as one which, when rotated, only produces other primes. Now, it doesn't actually give a definition of rotation of a number, but it gives enough examples that we can see that it just means taking digits from the beginning of the number and moving them to the end, or vice versa. Now, most of the heavy lifting for this problem is actually going to be done by our primes class, which we wrote in a previous series of videos. I'll put the links to those in the description if you're curious. We'll also need to implement this rotation operation, but other than that, the solution should be pretty straightforward. Just checking each of the primes less than 1 million to see if they are circular. So let's get into it. As usual, we'll copy our template directory to make our problem directory. But rather than opening our main.cpp right away, let's actually go to our makefile. We rarely take a look at the makefile because the template has it set up for the most common usage, but there is one flag that we're going to need to add. In particular, we need to link in our number theory library that has that primes class that I mentioned. So that's just this -l numtheory flag here. So now let's go to our main.cpp. Now, there are two different strategies, broadly speaking, that we could use to implement this rotation operation. The first, and maybe the most intuitive, is to just convert the number to a string and perform the operation on strings, and then convert it back into an integer. And that's a perfectly valid way of doing it. But there's a slightly more efficient strategy, which is to do it by dividing by and multiplying by powers of 10. And that's the approach that we're going to take. So in order to do that, we're going to need some powers of 10. So we'll just call it PO10. And we'll need the first 8. That's going to be 1, 10, 100, 1,000, 10,000, 100,000, 1 million, and 10 million. That's because we're only searching as high as 10 million, but we want to be sure if we go 1 past the end, we don't read past the end of our array here. So we'll just put the first 8 powers of 10 in our array. Now, in order to use this technique for rotating our numbers, we need to be able to count the number of digits in our number. So we're just going to write a little helper function, call it count digits. And this is just going to start with the smallest power of 10 and check each power of 10 until we find one that's bigger than our number. And so we'll say I, and I is going to go from 0 to PO10 of I, or while PO10 of I is less than or equal to n, then we're going to continue looping and incrementing I. And just as a quick check to make sure that we haven't made an off by 1 error, let's suppose that n was equal to 10. Well, in that case, when I would be equal to 2, or excuse me, when I is equal to 1, that would give us the first power of 10, that is 10, we would see that PO10 of 1 would be equal to n, and so we would continue looping until I is equal to 2, at which point we would break and return I. And that would be the correct answer. 10 has 2 digits. All right, so now that we have our little helper function, we can implement our rotation function. So we'll say uint32t rotate uint32t n. And we could either implement this by taking a digit at the left side of our number and putting it on the right-hand side, or vice versa. But it turns out that there's a little advantage to doing it one way versus the other. In particular, if we take numbers from the right-hand side and put them on the left-hand side, we automatically miss one of the failure cases, and that is if our number has any zeros in it, then by taking numbers from the right and putting them on the left, eventually that 0 will be the first digit, or the rightmost digit, which will make our number divisible by 10, and it won't be a prime, which is fine. Then we'll return failure that number is not a circular prime. If we do it the other way, however, and move digits from the left-hand side to the right-hand side, eventually 0 will reach the most significant digit and will artificially shorten our number. And so we can just avoid that failure case entirely if we move numbers from right to left versus left to right. Okay, so let's do digits is equal to count digits of n. Okay. So then we want to get the least significant digit, that is the digit on the far right. So we'll say uint32t LSD. Let's spell it out. Least sig dig is equal to n divided by 10. Oh, excuse me, n mod 10. And we'll say uint32t rest, that's the rest of the digits, is going to be equal to n divided by 10. Okay, so now we have to shift our least significant digit to make it our most significant digit. And just using an example, if we had a 3-digit number, we would need to multiply. You can see, I hope, that we would need to multiply it by 100 to put that into the thousands place there. And so we'll just do return rest plus PO10 digits minus 1 times least sig dig. All right, so that's our rotate function. Now we just need a function to check a particular number to see if it is a solution. So is solution. And this is where that primes class is going to come into play. So we'll call that primes p, and it's going to take a prime, call it lowercase p, and check to see if it's a solution. Now let me pull up that primes class. It's going to be under common primes.h. As I mentioned, we wrote this in a previous series of videos. And if you're interested in the details of the implementation, I'd recommend checking those out. But if we just want to use the class, we can just look at this public-facing interface here. And it's going to be this get prime and is prime, which we'll take advantage of. Get prime just gets the nth prime. So an argument of 0 would give us 2. An argument of 1 would give us 3, etc. And is prime just checks if a number is prime, as you might expect. Okay, so to check if a number is a solution, we just need to repeatedly rotate it and check all of the rotations to make sure that they're all primes. The way that we'll know that we're done is when we've rotated them to the point where we get our original number back. And so we won't want to change our original number here. In fact, let's make that const. We'll keep track of our current prime number in a separate variable. We'll just call that cur p, and the initial value will be p. Now we have to be a little bit careful here because our termination condition for our loop that I'm about to write is going to be that cur p is equal to p. Remember, we're going to rotate it repeatedly until we get our original number back. But we can't do that check right now at the start because they start off equal. And so we need a loop that will skip the check on the first iteration. And that's exactly what a do-while loop lets us do. So we'll just say do while cur p is not equal to p. And inside this loop, we're just going to want to check to see that cur p is prime. We'll say if p dot is or not p dot is prime cur p, return false. And then we'll just say cur p is equal to rotate cur p. And if we've rotated through all the possibilities and they're all primes, then we're just going to return true. Then obviously our number must be a circular prime. Okay. So now in our main function here, we just need our primes object. We need the index of the prime that we're testing. And we need to keep track of the number of circular primes that we've found. You'll recall that our final answer is going to be the total number of circular primes less than 1 million. So we'll say for I is 0, p dot get prime I is less than 1 million, increment I. And we'll say if is solution p dot get prime I plus plus count. Oh, and we will want to initialize that to 0. And then we will just print out count equals count. Now, there's one more thing that I usually like to add in my solutions, which is not strictly necessary, and that's just a little sanity check to make sure that we haven't made any simple mistakes. We'll just print out each circular prime as we find them. So we'll just say p dot get prime I. There were several examples given in the problem description here. So these are the circular primes less than 100, and so we would expect to see those show up in our solution. Also, this number 197 is an additional example that we would expect to see. And one final note before we test this, you may suspect that this get prime function does a lot of expensive work. Calculating primes isn't trivial. And so you might be concerned that I'm calling this get prime multiple times rather than caching the result. But actually, one of the great features about our primes class is it does that for us. The whole point of the primes class is to, among other things, cache our primes calculations to make them more efficient. So we don't have to worry about calling it multiple times with the same value. All right, so let's go to our problem directory and make. Let's see, it looks like I've made some minor mistake. Just missed a comma here. Also, while I'm up here, I'm just noticing I didn't, in fact, include primes.h. So that would have been a problem. Looks like it's built and it's run. It's given us an answer of 55. Let's just check. We see our number 197 is in fact in the list. It looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers less than 100 as expected. So that passes our sanity check. So now let's see if our answer is correct. Just pull up the archive here, go to problem number 35. Again, it's signed me out. I've had this happen in a couple of problems where while I'm recording, it signs me out. So then we just gotta move this off screen while I enter in my password here. Don't want anyone breaking into my very important Project Euler account. Okay, and now we can scroll down to problem 35 and verify that our solution is indeed correct. So thank you for joining me in this video. In the next video, we will tackle problem number 36.